Section 13.3, the arc length and curvature. Remember from algebra classes, when you were on a straight line and you were asked to find the distance, you would use this formula, which basically comes from constructing this right triangle. So this would be like, let's say, absolute value of x2 minus x1. That would be absolute value of y2 minus y1. So if you use the Pythagoras theorem, lo and behold, you get the distance formula. But the question is, what if you're on a curve, whether it's on the floor or the curve is in space? How would you find the distance between 2 points on a curve, which is known as arc length? So let's examine what happens when you are on the floor. In other words, what happens if you are in R2? Okay. So what we do, we take these line segments, in other words, we subdivide the curve into many line segments. And those are called secant line because anytime you take a curve and connect two distinct points on the curve together, the result is called what? Secant line. So what happens is, if you take 2 points, let's say x1, y1, x and y, and you increment what? X and y by the amount of delta x and delta y to get to the next point on the curve, like let's say P2, then you can what? Find out what this the length of this hypotenuse is based on this right triangle. So delta S, remember delta S is the length of the secant, not the what? Arc length. So we're going to show the arc length with delta L, and we're going to show the secant line with change in secant line with delta S. So delta S is the change in secant line, whereas delta L is change in the arc length, correct? So delta S squared equals delta x squared plus delta y squared. So delta L, if delta x and delta y is small enough, they can be approximately the same. So in other words, we can approximate delta L, which is the change in arc length, approximately equal to delta x squared plus delta y squared. As I mentioned, if these two quantities approach to zero, delta L gets closer to what? Dx squared plus dy squared. Remember, delta x is the same as dx, delta y is the same as dy. So if you add up these, the length of these little pieces of line segments, and let delta what? Let I go from, let's say, let's say from 1 to infinity. So that means you add infinite number of line segments. Lo and behold, that would be the same as what? Limit of sum of these line segments as n approaches to infinity, where I goes from 1 to n. And lo and behold, you have the formula, which is AL, the arc length, is equal to what? Integral from a to b, so that will be the limits for x, square root of 1 plus what? F prime of x squared dx. This is what we did in previous classes. However, if the curve is what? Expressed parametrically, like so, then the formula 1 plus f prime of x squared changes into what? Square root of dx dt squared plus dy dt squared, where t goes from a to b, correct? In 3 dimension, we have what? Let's say this is the parametric equation of a curve in 3 dimension, where t goes from a to b, then the formula becomes L, which is the arc length, equals antiderivative of a square root of dx dt squared plus dy dt squared dz dt squared. And then the integral is taken with respect to t. However, this right here, the radicand under the radical is also absolute value of the velocity, which is kind of like the speed. In other words, if this was the position of a moving object on a space curve, so the arc length can be obtained by integrating the speed with respect to what? Time. And of course, this would be in a scalar. So this is like a number, correct? If you remember way back in previous sections, we talked about this infamous curve, cosine sine t, which is called helix. And this is how it looks like. So the name is helix, right? It's kind of like a spiral which wraps around the z-axis because the z component has a t. If t was anywhere else, then the spiral will wrap around that particular axis. Anyways, the point is, if you go from 0 to pi over 2, let's say from point P1 to point P2, let's say at this point t is equal to 0, at this point t is equal to pi over 2. In other words, the moving object has traveled on this helix from time 0 to what? Pi over 2 seconds, this much. Can you find that distance? Of course. So the idea is what? X is equal to cosine of t, y is equal to sine of t, z is equal to t, where t goes from 0 to pi over 2. So these are the parametric equations of the curve what? Helix, and I got it from here. What I have to do is take the derivative of these guys one at a time with respect to what? T. So that will be cosine of t, and dz dt, that will be 1. Now I'm going to substitute these, these guys, these equations into the formula, and I'm going to end up with what? L equals what? I'm going from 0 to what? Pi over 2 square root of, now you have to square these guys. So that would be like what? Negative sine t squared plus cosine t squared plus 1 squared dt. Because remember, the formula is dx dt squared plus dy dt squared plus dz dt squared. Now, sine squared plus cosine squared from trigonometry classes is just 1. So this guy is 1 plus 1 dt, and you're going from 0 to pi over 2. So the answer is the square root of 2 pi over 2 minus 0, which is what? Square root of pi, square root of 2 pi over 2, and this would be like units of distance. And notice it's a positive number because it represents the distance. So that means if the moving object travels from point A to point B, or from point P1 to P2, this is how much that object has traveled between the times 0 second and what? Pi over 2 seconds. Okay, the next topic is called curvature of a smooth curve in space. So we'll define curvature momentarily, but let's define what they mean by a smooth curve. A smooth curve is a curve whose parametric equation is given by r of t, is said to be smooth if r prime of t is not equal to what? 0 vector for any t, correct? So if we take the derivative of the parametric equation of the what? Curve, you should not find any value of t which would make this not 0 the number, but 0 the vector. In other words, this would be an example of a smooth curve, but this is not. Why? Because you have a sharp turn here, correct? This guy is smooth, but it's piecewise smooth. In other words, every piece is smooth, but the overall curve is not smooth because you have a gap between these 2 points. So the curvature is what? Is denoted by the Greek letter kappa. That's how you write kappa. And then it's a positive number. and by definition is magnitude of dt ds, whereas t is the unit tangent vector on the curve, and ds is the change in the arc length. So the magnitude of the what? Rate of change of unit tangent with respect to arc length is by definition the curvature, correct? So curvature is the rate of change of the unit tangent vector with respect to arc length. However, what does it do? I mean, why do we have to care about curvature? Curvature measures the degree of how much bend do we have on the curve. So it measures the amount of bend on the curve. And this phenomena is used on theme parks like roller coasters and so on and so forth. So curvature tells you how much bend. So it measures the amount of bend on the curve. Okay, the problem is this guy, and remember what the definition of the unit tangent vector was. It was derivative of the what? Position vector divided by its magnitude. For practical purposes like homework assignment, we don't use this formula right here because it's hard to use this. Instead, we use this nice formula, which says the curvature will be a function of t, provided what? You are dealing with what? Parametric equation of the line in, and the parameter is t, is magnitude of r prime cross product with r double prime over magnitude of r prime to the power of 3. So this is a very nice formula which directly finds the curvature without knowing what the unit tangent and arc length is. This is a really nice formula. Let's go back to our, the good old example here, which is once again arc length. And we like to know what would be the curvature at this point. In other words, how much bend do you have right here? So to do that, I need to use this formula. So what I do, I go, okay, what is r prime of t, which is what? Minus sine of t cosine of t 1. What is r double prime of t, which is minus cosine of t minus sine of t and 0. However, because I'm trying to find out how much bend I have at exactly at point P, so I'm going to what? Replace the t's with pi over what? 2. When I do, I get r prime of pi over 2 equals what? Negative 101, and r double prime of pi over 2, I get 0, negative 1, 0. So according to the formula, now I'm supposed to take what? The cross product of these guys evaluated at pi over 2. So that will be I, J, K, and then negative 1, 0, 1, and then 0, negative 1, 0. And lo and behold, you get 1, 0, 1. So now we have to take the magnitude of r prime evaluated at pi over 2, the cross product, this guy right here. And as you can tell, the answer is the square root of 2. Because that would be 1 squared plus 0 squared plus 1 squared. That would give you a square root of 2. Okay, then, we're almost there now. So the curvature at pi over 2 equals magnitude of this cross product, which is a square root of 2, divided by magnitude of r prime, which is this guy right here. And the magnitude of that guy is what? Square root of negative 1 squared, 0 squared, plus what? 1 squared, which is still a square root of 2, but I have to raise it to the power of 3. So when I do, I get 1 over what? Square root of 2 squared. One of these guys cancels one of those guys. And lo and behold, you get 1/2. So that would be how much bend you have on this curve, so-called helix, at point P, where T is equal to pi over 2. But the question is, what is this? I mean, like, how do I know how much bend you have? Okay, so the answer came up to 1/2. So what? Well, one of the things which I like you guys notice is what? A line has no curvature. Why? Because everywhere on the line, the curvature is 0, since on a straight line, we have no bend. Okay, what about circle then? Well, this circle, okay, when it's drawn on what? On the curve, tangent to the curve at that specific point, it has a name, it's called Osculating Circle. And the radius is shown by the Greek letter rho. So this is a Greek letter rho, okay? Osculating in Latin means kissing. So that means the circle has to touch the curve or to be tangent to the curve at that specific point which you're trying to find the what? Curvature for. So what we do is the following. The curvature of an osculating circle is what? Equal to reciprocal of the what? Radius of the what? Osculating circle. In other words, what we're saying is, the smaller the what radius, the higher the what curvature, or the higher the radius, the smaller the what curvature. So the greater the radius, what? Smaller the curvature, the smaller the radius, the greater the curvature. That's basically because they have a reciprocal relationship. So anyways, the point is this. So to just make some sense out of this guy, so what we do, we draw this osculating circle at point, let's say P, correct? Okay. But what is the radius of that osculating circle? Remember, it's a reciprocal of the curvature. The curvature was 2, 1/2. So the radius of the osculating circle is 1/2, which is 2. In other words, now you can get a sense of how much bend you have on this curve helix at that point based on the circle. So the bend is as much as if you would draw a circle whose radius is 2. So that gives you a clue how much bend you have, so you can make some sense out of this. Otherwise, it's just a number which we don't know what to do with. So that's basically the purpose of this osculating circle, correct? Notice the radius is reciprocal of the curvature at that specific point. All right. So, so the idea is, what if you have the curve is given to you in terms of function of x? If that's the case, then you have this formula, which curvature, now it's a function of x, not t. Okay, this is absolute value, correct? Absolute value of f double prime divided by 1 plus f prime quantity squared, this guy, to the power of 3/2, correct? So the idea is as follows. Just suppose, you like to kind of find the curvature of a parabola at 0, right about here. How much bend do we have? That's what curvature is all about. Turns out there are 2 ways to do it. One way would be parameterize this. So parameterizing the curve is not one of a kind. So the way I would parameterize this, I would let x to be t, y to be t squared. And looks like t goes from -infinity to infinity to cover the entire parabola. Then you would use this formula, curvature, t equals magnitude of r prime cross r double prime over magnitude of r prime to the power of 3. And you would get an answer. Remember, you're trying to find out what the curvature is at 0, 0. But remember, x is equal to t, so if x is 0, so is t. So evaluate this as, so find out what curvature is at 0. Okay, the alternative is use this formula. So what you do is what? Kind of take the derivative. Okay, so that would be f of x is equal to x squared. So f prime of x is 2x, so f double prime of x is 2, correct? Then you use this formula at what? 0 to find out what the curvature is. So that would be absolute value of 2 over. Denominator is 1 plus what? 2x quantity squared, and then the entire quantity to the power of 3 halves. Remember, we're trying to evaluate this at 0. Okay, so we get curvature of the parabola at 0 is 2 over. This guy goes to 0, so you'll have 1 at the bottom, so it's 2. So once again, the question is, what is this? What did I find? Okay, the curvature of the parabola at the vertex when the parabola is opening up and the vertex is at the origin is 2. But how much bend do I have? As I said, draw the oscillating circle. Okay, and make sure it's what? Tangent to the what? To the point. And guess what? The radius of this oscillating circle is a reciprocal of the curvature, so it will be 1/2. So the bend is as much as what? A circle whose radius is 1/2 and it's tangent to this point, which we're trying to find the what? Degree of the bend of the curve. The other one is what? This problem, which is y is equal to natural log of x, correct? So how would you find the curvature of a natural log of x at x equals 1? First of all, the graph kind of looks like this, and it hits the what? X-axis at 1, correct? I'd like to know how much bend I have at this point. What is the amount of bend of this curve, natural log of x, at 1? So you can parameterize this if your heart desires. The way you would parameterize this is as follows. So there are 2 ways to do this. So one way would be like so. If y is equal to natural log of x, so that means x is equal to e to the power of y, correct? So to parameterize, one way would be let y to be t, so x would be e to the power of t, correct? And t has to be a positive number because e to the t, which is x, is always positive. Do you see it? Okay, which in turns is x. That's one way to do it, and then you use that magic formula and you're good to go. The alternative is use this formula right here. So what you do, you take the what? Derivative of natural log of x, okay, which is what? 1 over x, correct? Take one more derivative, and that would be negative 1 over x squared. And now curvature at any point on the graph of natural log of x is absolute value of negative 1 over x squared over 1 plus f prime of x squared, which is 1 over x squared to the power of 3 halves. But remember, we're trying to evaluate this at this point, 1, 0. So evaluate this at x equals 1. And lo and behold, the curvature at 1 comes up to square root of 2 over 4. So there you have it. Once again, the question is, how much bend do I have? What you do, you draw as what? Escalating circle here, such that it will be tangent to the what? Curve at that specific point you're trying to find the amount of bend. And remember, the radius of the oscillating circle is reciprocal of the curvature, correct? So that would be 4 over square root of 2, which is the same as 4 square root of 2 over 2, which is 2 square root of 2. So it's as much as what? The bend is as much as if you had a circle here whose radius is what? 2 square root of 2. Thank you.